Section: Introduction. In this section, we explore the capabilities of large language models, LLMs, and the underlying mechanisms that drive their performance across different tasks. While LLMs have shown impressive abilities, we recognize that their internal workings are not fully understood. Different fields require unique knowledge and reasoning, which means LLMs must adapt their decision-making in real time for various queries. This adaptability is especially important in high-stakes areas like law and medicine, where mistakes can have serious repercussions. Our research question focuses on how LLMs modify their reasoning and decision-making across different domains, which is different from existing studies that mainly look at how LLMs retrieve factual information. These studies often miss the complexities involved in generative tasks. By understanding how LLMs adjust their reasoning in these tasks, we can improve transparency in their decision-making, enhance our understanding of their generalization abilities, and foster collaboration across disciplines. We specifically examine the patterns that models exhibit when facing domain-specific challenges, rather than just retrieving facts. Recently, we evaluated GPT-4's ability to infer domain knowledge using a React-based LLM chain, generating reasoning paths from unlabeled coding examples without explicit domain descriptions. Our findings indicate that GPT-4 significantly outperforms its generic version when provided with relevant examples, suggesting it can grasp the essence of the domain. However, it remains uncertain whether the model genuinely understands the content or simply mimics the examples. We also look at how hidden states represent context for domain-related queries before generating responses. Our goal is to see if models inherently encode general natural language for specific domains. Unlike previous research focused on closed-ended tasks, we investigate hidden states in open-ended scenarios, which helps us better understand domain nuances across various LLMs. Our results highlight the effectiveness of hidden state activations as representations of domains. We analyzed hidden state traces across multiple LLM architectures, such as Gemma, Phi, Mistral, and Llama, and found consistent patterns in domain-specific activations, regardless of prompt styles. This consistency indicates that hidden states capture essential domain characteristics rather than just superficial text features. We also compared our findings with traditional methods like semantic routing and token-based classification, showing that internal model representations can offer significant advantages for domain interpretation. Our main contributions include demonstrating that hidden states in LLMs capture robust domain-specific information across different architectures and prompt variations. We refer to these signals as latent domain-related trajectories. Furthermore, we show that these trajectories remain stable across various tasks and models, which opens new avenues for efficient model selection, particularly in cross-domain generalization tasks. Our experiments reveal that using latent domain-related trajectories for model selection leads to notable performance improvements, especially in open-ended tasks. In summary, we aim to deepen our understanding of how LLMs can distinguish between queries from different domains and the value these representations provide compared to traditional semantic and token-level methods. Section Summary. In this section, we explore how large language models, LLMs, adapt their reasoning and decision-making across different domains, emphasizing the importance of understanding their internal mechanisms for applications in high-stakes fields like law and medicine. Our findings reveal that hidden state activations consistently capture domain-specific information across various LLM architectures, enhancing model selection and performance in open-ended tasks compared to traditional methods. Section: Preliminaries. In this section, we outline our preliminary definitions and operational terms used in our experiments to evaluate how well large language models, LLMs, capture domain-specific representations. We focus on hidden states generated during the prefill phase, which is when the model processes input tokens to create intermediate states before producing the first output token. Hidden states are the intermediate activations from each layer of the model as it processes input tokens, helping to build its contextual understanding. For each query, the model produces a set of hidden states shaped by the number of samples processed at once, the size of the hidden representation, and the total number of layers, each generating its own hidden states. To simplify our analysis, we calculate the mean activation across both the batch and dimension axes for each layer, resulting in a single vector that reflects the average behavior during the prefill phase. We also compute the variance of activations for each layer to understand how much the hidden states vary across samples and dimensions, which gives us insight into the sensitivity of different layers to input variations. In some cases, we use standard deviation instead of variance by calculating its square root. We refer to latent domain-related trajectories as the patterns in hidden states that correspond to specific domains, such as biomedical, law, and maths. By analyzing the mean and variance of activations across layers, we can trace how the model represents domain-related information. These definitions help us quantify the informativeness of hidden state activations, allowing us to explore whether they encode meaningful domain-specific knowledge before generating outputs. Our motivation stems from the observation that queries from similar domains tend to cluster closely in terms of hidden state activations. This clustering occurs for both mean and variance across layers, indicating that the model shows similar confidence when processing queries from the same domain. Based on this, we propose that LLMs hidden states encode generalizable representations for specific domains, revealing traces of domain-related information from the context understanding phase. To test this hypothesis, we aim to determine if this ability is consistent across different LLM architectures, training methods, and model parameters. We also want to see if these representations persist after fine-tuning and how robust they are when prompts are altered. We develop a method to benchmark model performance using these hidden state representations against traditional approaches, quantifying their value compared to token-based and semantic representations. Our experiments and analyses will provide evidence for our hypothesis and evaluate the robustness of hidden states across various models, prompts, and domains. In our experimental setup, we test our hypothesis through controlled experiments focused on generation and performance in 3 critical fields: healthcare, finance, and law. We begin by describing our setup and the scenarios we considered. We utilize the DeBerta encoder model and 4 different pre-trained LLM architectures available on Hugging Face, including Gemma 2B, Phi-3 Mini 3.8b, Llama 2-7b, and Mistral 7b. These models were chosen for their effectiveness across various tasks and their differing dimensions and training methods, allowing us to explore generalization in our findings. All experiments are conducted on 4 NVIDIA RTX A6000 GPUs. We leverage the multi-domain nature of the MMLU dataset, selecting 30 subtasks from the 57 available. To avoid ambiguity, we grouped overlapping domains into 4 supercategories: mathematics, biomedical, law, and humanities. We refer to the queries from these distributions as the base pool, consisting of 7,358 samples. Additionally, we include a specialized pool with domain-specific datasets that cover overlapping domains, such as GSM-8K for mathematical reasoning, MED-MCQA for medical subjects, CaseHold for legal holdings, and the Plato dataset for identifying philosophical terms. For our comparisons, we evaluate our approach of using LLM hidden states as domain representations against 2 baselines, a semantic layer and a DeBerta classifier. The semantic layer selects models based on similarity scores from few-shot utterances, configured with 4 main roots corresponding to the dataset domains. We used 1,000 utterances for each root, totaling 4,000, and employed the default configuration of the Hugging Face encoder class. We also fine-tuned a DeBerta encoder for a sequence classification task with 4 output labels, training it on 4,000 samples from the MMLU domains. We chose DeBerta for its strong performance in various NLP tasks, particularly as an encoder model. Section Summary. In this section, we define key operational terms related to our experiments on LLMs, focusing on hidden states generated during the prefill phase to assess domain-specific representations. We outline our hypothesis that these hidden states encode generalizable domain-related information, and describe our experimental setup using various LLM architectures and datasets to evaluate their performance across critical fields like healthcare, finance, and law. Section: Latent Domain-Related Trajectories. In this section, we analyze the capabilities of the hidden states in large language models, LLMs. Our goal is to determine if the ability to encode domain-specific information in these hidden states is a general feature of LLMs, rather than something unique to a specific model. To explore this, we compared several generative LLMs, including Gemma 2B, Phi 3 Mini 3.8b, Llama 2-7b, and Mistral 7b, alongside a pre-trained encoder model, DeBerta, focusing on the contextual representations during the prefill phase. We structured our investigation around two main questions. First, how do the hidden states of generative models compare to those of an encoder model that captures detailed semantic and positional information? Second, after fine-tuning on specific tasks, do LLMs maintain their domain-specific hidden state patterns, or do they change significantly? To address these questions, we randomly selected 5,000 samples from a collection of domain-specific queries and input them into the various models. We extracted hidden state activations from each layer, concentrating on the last token of the input query. This process was repeated for all layers to ensure a thorough analysis. Additionally, we included another 5,000 samples from a different distribution to confirm that our findings were not simply due to similar instructions or query semantics. Our analysis revealed several key trends. First, the DeBerta model did not show a clear pattern in its traces, likely due to its bidirectional architecture, which combines context from both sides, resulting in less predictable activations compared to autoregressive models. In contrast, the hidden states of autoregressive models consistently clustered around domain-specific queries, indicating their ability to differentiate between domain-related requests. We also observed that the variability in hidden state traces was consistent across all models, suggesting that these differences were more related to the datasets than to the model architecture. Furthermore, when we examined fine-tuned versions of the Phi 3 Mini 3.8b and Llama 2-7b models, we found that the domain-specific traces remained largely unchanged, indicating that these properties persist even after fine-tuning. To further test the consistency of the traces against changes in prompt structure, we created 3 new domain-related pools from various datasets in the medical, maths, and law domains. We applied different prompt templates to see if the traces varied with prompt changes. Our findings showed that early layers exhibited some sensitivity to prompt variations, especially in the law domain, while deeper layers stabilized the representations, maintaining domain-specific information despite prompt perturbations. Overall, our results suggest that LLM hidden state traces provide a reliable representation of domain-specific information, which remains largely unaffected by changes in prompt style. This stability indicates that hidden state-based representations could be valuable for understanding domain context and could be applied in various areas, including cross-domain model selection. Section Summary. In this section, we investigate the ability of various generative LLMs to encode domain-specific information in their hidden states, comparing them to a pre-trained encoder model. Our analysis reveals that while generative models consistently cluster around domain-related queries, the hidden state representations remain stable across different prompts, indicating a robust capacity for capturing domain context that persists even after fine-tuning. Section: Benchmark with traditional methods. In this section, we benchmark traditional methods by utilizing domain-specific traces. We set up our experiment with 3 fine-tuned versions of Phi 3 Mini 3.8b, focusing on emotional, mathematical thinking, and medical data subdomains, which we collectively refer to as Phi 3 domain. We performed zero-shot evaluations on these models using the LM_eval library with samples from the base pool, confirming that each model is effective in its domain. We identified the best-performing model for each domain: Phi 3 MATHS for mathematics, Phi 3 MEDICAL for biomedical, and Phi 3 Pretrained for law and humanities. To analyze the hidden states, we employed a multi-layer perceptron, MLP, and compared it with a semantic layer and a DeBerta classifier. We trained the MLP using hidden state traces from 4,000 random samples, maintaining a consistent learning rate and weight decay across all methods. We also included a baseline LLM sequence classifier, which processes the entire input, to compare with our LLM hidden states classifier. We tested 5 different datasets that were not part of the training to evaluate the final performance of each method, as shown in our results table. The LLM hidden states classifier consistently outperformed the fine-tuned models and other baselines, especially in open-ended tasks like GSM-8K and domain-specific tasks like MEDMCQA. Interestingly, the hidden states classifier often surpassed the fine-tuned models, which might seem surprising since we would expect fine-tuned models to excel in their trained domains. This could be due to overfitting in fine-tuned models, limiting their generalization across different tasks. The hidden states, on the other hand, provide richer representations, enhancing cross-domain generalization. We also tested the MLP classifier on hidden states from the DeBerta model, which performed poorly. This aligns with our findings that DeBerta's hidden states lack clear patterns across domains, making them less effective. Our results suggest that autoregressive models like Phi 3 Mini 3.8b are better at capturing domain-related trajectories than encoder models like DeBerta. Furthermore, we compared the LLM sequence classifier with the LLM hidden states classifier. Our findings indicate that separating input analysis from the generation phase, as done in the hidden states approach, yields more robust representations. The hidden states capture detailed information about the input, improving prediction accuracy, while the generation process can limit domain representation. In summary, we found that moving away from strict domain-labeled model selection towards hidden state representation approaches enhances generalization across various domains and input types. Regarding the trade-offs of reducing layer computation, we explored how performance changes as we decrease the number of hidden layers used in the MLP classifier. Our experiments showed that while layer 26 marks a turning point for performance improvement, the best results come from using all 32 layers. This is because later layers maintain domain-specific representations, and incomplete representations can lead to performance drops, particularly in tasks like GSM-8K that require open-ended generation. Section Summary. In this section, we benchmarked 3 fine-tuned versions of Phi 3 Mini 3.8b across different domains and found that our LLM hidden states classifier consistently outperformed these models and other baselines, particularly in open-ended and domain-specific tasks, suggesting that hidden states capture richer representations for better cross-domain generalization. We also explored the impact of reducing hidden layers in the MLP classifier, determining that while fewer layers can reduce latency, the best performance is achieved by utilizing all layers, as later layers maintain crucial domain-specific information. Section: Limitations. In this section, we acknowledge several limitations of our study, which offers insights into hidden state representations in large language models, LLMs. First, we focus on smaller LLMs, specifically those with up to 7 billion parameters. While we show that even these smaller models can yield valuable information for domain interpretation, we have yet to explore how our approach applies to larger models. Additionally, the domain traces we present for each model may not fully capture the essence of that domain. Instead, they might reflect a mix of various subdomains based on the queries. As a result, the clustering we observe may not apply to other datasets with the same domain label. However, we believe this variability illustrates how the model adapts to new data distributions. This feature is a significant advantage of using hidden states for interpretation, as it enables us to receive direct feedback from the model itself.